welcome back. So this is the second lecture, DC machines and batteries. So I'm going to build on top of what we had covered last lecture. So that is the relationship between magnetism and electricity. We had thrown around a couple of principles, right? We had even looked at the geometry or orientation of magnetic fields and electricity, how they all play out to make what we call DC machines. We are still building on that simple basic principle, the relationship between electricity and magnetism. So today let's kick off the lecture with basic principles of electromagnetism. Before we go there, let us look at something. That's what we call a bar magnet, right? A bar magnet. A bar magnet. A bar magnet, think of it as a permanent magnet. Let's say this is the North Pole and the South Pole. So a bar magnet constitutes of two regions. This is what we call the North Pole. This is the North Pole. And that's what we call the South Pole, right? So this is the North Pole and that's the South Pole. So this bar magnet has some interesting features we need to jot down and put aside before we continue to electromagnetism. So this, if we happen to have iron filings, I'm calling them iron filings, excuse my art isn't that good. We would find out that we have iron filings that are concentrated in certain regions where the magnetic field, or the magnetic strength of the magnet is the strongest. We call these lines magnetic flux. Lines that represent the flow of magnetic fields and where the magnetic fields are the strongest. So we realize that for a typical magnet, so this is where we experience the strongest forces around the magnet, even around here, right? So forces strongest. So this is where the forces are the strongest, emanating from the magnet, right? So we tend to have an imaginary line. We can draw out a line that cuts across and is along the direction of the resultant magnetic field. So this is what we call magnetic. That's the axis of the magnet. This is very, very, very important to keep in mind. So let's put this aside. Let's jot it down and put it aside and proceed with electromagnetism. All right. So having noted this down, let's go back to the current carrying conductor. Let's go back to that. So let's say we have a conductor like so, conducting a certain current I, right? Let's say this conductor is of a certain length. Let's say the current I is the one flowing there. So of a certain length L in meters, whereby I is the current flowing, L L is the conductor length. Current is in amps. Length is in meters, a couple of meters, right? We'll look at that. So remember we said with the right hand grip rule, that's which states holding, making a fist, stretching out the thumb, right? Holding your arm straight in a way that the thumb is in the same direction as the flow of current. So the way your fingers curl around that denotes the direction of the magnetic field around the conductor. Guys, we already know that a current carrying conductor develops a magnetic field around it, whose direction is determined by the right hand grip rule. All right. So with the right hand grip rule, with my thumb pointing in the direction of the current, let me just draw one loop, just like so. That will be the direction of the magnetic fields, right? Like so. Let me fix it. All right. All right. So, and the fields, like so, like so, curl around like that. So the fields are strongest. This is where they are strongest, close to the conductor. So close to the conductor, the magnetic fields get stronger and stronger and stronger. So far away and far away from a conductor, the magnetic effects will get weaker and weaker and weaker. So that's very important to keep in mind. So let's say this is just one conductor. What if what if what if what if we make a loop? We make a looping conductor. Still it's a conductor, but let's say we loop it. Let's say we make a loop out of it, right? So let's say we have a loop out of it. Let me demonstrate. Allow me to demonstrate what a loop looks like. All right. So this is the conductor, right? So it almost fits, right? So this is the conductor we have. So we say if we have a current flowing through that conductor in, let me try to hold it. Yes, in that direction, so the magnetic field around this conductor will develop around it in like so. So let's say now, instead of holding it straight, we curve it around and make some kind of a loop. Let's say we hold it like so and we make some kind of a loop. So let's say this is the loop. All right. So that's the loop. So how would it behave? How would it behave? How would, remember with DC machines or any other electromagnetic machine, orientation matters. How you orient everything changes the end result, the behavior, right? So let's say we have a looping conductor. Let me draw it like so. Still, the length is going to be the same. The total length of that loop is going to be the same. So let's say we have current flowing in that direction. It will go around, then come back like so. So this is the current I. So the magnetic fields around it, this time round, they are going to be like so. So they are going to be like this, like that. So like this, right? Up and down. So this side, it's going to be like this. So it's going to be down and up. So that's how things are going to happen. But look at what's happening in the middle, right? So it's like magnetic fields are combining right in the center and emanating back out, then again. Out, back, then again. So like so, right? So out, then again, loop around, loop around, loop around. So that is how a conductor, one loop, would behave. That is how the loop would behave. So let's look at something else. Let's look at something else. What if instead of one loop, we make a number of loops? Let's say instead of one loop, we make a number of loops, or increase the number of turns around the loop. So let's try to visualize more loops, right? So the way I'm going to visualize them is like so. Let's call this a multi-turn loop. What happens with a multi-turn loop? Let's say we start with a conductor and make more loops out of it, right? And end like so. We've realized that if, let's say, current is flowing like so, it will go down and up, right? Down, up, down, up, down and up, down and up, right? So down and up, down and up, then down, right? So let's say we have applied the positive voltage to point A. Let me label that as point A and point B. So point B is the one that's negative with respect to point A. So let's look at this. What does this tell us? So this tells us that let's apply again the right hand grip rule. So the right hand grip rule around a coil of this nature. So this is what we call a solenoid. It's a coil that can generate magnetic fields to turn into what we call an electromagnet. Unless a bar, this is mostly commonly known as a permanent bar magnet. Bar magnet, right? That's also known as a permanent bar magnet. So this is going like so. So that means we are going to have that as our north, that as our south. So we are going to end up with what we call an electromagnet. A magnet like the other one. So this is its magnetic axis. Magnetic axis. That is its south region. That is its north region. So guys, we've found a way to create a magnet out of electricity and a coil of wire. Very, very important. It will behave like the bar magnet with some changes that we are going to look at in the next lecture.